z plus z squared minus z cubed. So the z and minus z cancel out, and the 2, so we get 1, because 1 plus 1, 2, plus 1/2. And then you have 1 minus z squared minus z cubed plus z to the power 4 minus z to the power 5 plus z to the power 6 minus z to the power 7 plus dot times sigma f sub r of n over r factorial. Sorry, z to the power r. So this is 2. Now open up parentheses, and you get the following: f sub r of n. And this is only an illustration. This can be done for any atomic event, any die, even infinite die, minus over r factorial. Now collect terms. This is f sub r of n over r factorial plus 1/2 f sub r minus 2 of n over r factorial. You compare coefficient of z to the power r on the left and the right. There's only one here, and minus 1/2 f r minus 3 n over r factorial plus It's an infinite order recurrence. You can, and at the end, but you only need, for any finite r, you only need finitely many terms. So that's another way of cranking out many things. And doing this, we get this. We have the difference of f sub r n plus 1 minus f sub r n equals this. So if you know the previous values of these polynomials, and then you can just sum this and do indefinite summation and get explicit formulas. But how to prove this rigorously? You just plug it in. And you only want to prove the leading terms, the da-da-da. So you do 2 cases, for even and for odd. So you have to split it up. Case 1 with even, case 1 with odd. And then you have it. This will already will not show up for the leading terms. So this will be a completely rigorous proof. But I claim that even this isn't too much to do. I was too nice in the Zeilberger. I gave too many details. Because we know a priori that such a recurrence does exist. We don't really even have to exhibit. We know how the recurrence looks like. And for a recurrence of this type, if you check enough special cases, you have a rigorous proof. So it's an example where you have a completely rigorous proof just by guessing. The fact that you were able to guess this thing, it's not a priori clear that you could guess it, but to guess it because you have factorial, you can divide, it's a completely routine verification. So you don't even have to do it. But it's no big deal, the computer can do it in 1 second, and maybe it's more convincing to actually do this. So this was a warm-up of proving the central limit theorem for using completed computers. And I have a paper about it that does this. Now we go finally to the paper itself. So here the population is not coin tosses. Here the population are permutations. So let me remind you, what is a permutation? Something terrible happened. And this person I watched. Oh, here it is. Okay. So, in real life, by the way, statistics. Usually statistics is about people. Or anything else, objects. And you have a finite population of people. You take the weight, height, IQ, and so on. And you try to find averages and standard deviations. And if you fancy, you try to compute moments. But sometimes you can do statistics on combinatorial objects. So if you take permutation, there are two important main permutation statistics for permutations. The first one is the more famous one, is the number of inversions. This features in the definition of the determinant. It's simply given permutation of n letters is the number of times you have big in front of small. But it doesn't have to be right away. So let's do a good example. So, okay. 4, 5, 1, 3, 2. So this is an inversion. 1, 2, 3. Yeah, so 3. And the another one is called the major index. Was introduced by Percy Alexander McMahon about 100 years ago. It's the major index. He did not call it the major index. He was a major, by the way, in the Royal Artillery. But he was a very modest man. He did not call it after himself. He called it the greater index. And the great French combinatorialist, Dominique Foata, called it in French, in this major, and that high, in English became major index. So it was an unintentional pun, according to him. But now you can think of it is named after Major McMahon. Anyway, the other statistics, the major index, is you look at all the immediate descents. Whenever something is bigger of its neighbor right after it. But you don't just count them, you add up the places. So that's the second place, and that's the place number 4. You add them up, and you have another numerical attribute of permutations. Now, combinatorialists like to have generating functions. It's the probability generating function. You want to find what the probability if I pick a random permutation on n letters will have exactly 11 inversions. So you look at the probability, which is you look over all the permutations. You ask each of them, how many inversions do you have? And you put Q to this. That's a weighted numerator. And to make it probability, you divide by the number of permutations. This is the probability generating function for the so-called number of inversions. And in 19th century, combinatorialist or mathematician, it was more than that, called Netter, proved the beautiful closed form expression. There is no closed form expression for the number of permutations on n letters with exactly I inversions. No. But for the generating function, and if you take the coefficient of q to the power something, you get exactly the probability is beautiful. It's 1 minus q times 1 minus q squared. It's a beautiful product formula. It's the q analog of the factorial function. So it's really 1 times 1 plus q times 1 plus q plus q squared to this beautiful, beautiful formula. Explicit formula for the probability generating function for nice, beautiful product formula. And what McMahon proved is the same thing is true for the major index. In other words, they are equally distributed. So the probability of taking a the probability of picking a permutation uniformly at random and getting the inverse number of inversions is 11 is exactly the probability of getting the major index to be 11. They are equi-distributed. And it's not such an easy theorem. And it's a beautiful combinatorial proof due to Dominique Foata. The same Foata I'm talking about. A seminal published in 1965 in the Proceedings of the American Mathematical Society that back then had better editors with better taste. That's why Andrew Baxter and I decided to submit it because it was referenced this paper. This has no direct bearing on the problem itself, but it was a major breakthrough in this subject. Then